Assalamu alaikum. Welcome to lecture 24 of natural language processing. Today we will continue with our discussion on the encoder decoder model, which we introduced last time. And we introduced this model in the context of machine translation, which is one of the most popular application of natural language processing. So we will be discussing the encoder decoder model in the context of RNN as well as transformers, and we will be discussing the beam search idea, which is applied oftentimes for decoding, and we will also then discuss evaluation of machine translation. So this is basically the agenda for today. We have a quiz, the last quiz today at the end of class at around 11. At around 11. So this is all chapter 10 of your textbook. So please go over the textbook as well. All right. So let's get started. So we were talking about the encoder, the decoder model. So as the name suggests, this consists of two models, one after the other in series. And in the context of sequences, these models are also sometimes called sequence to sequence models or sec to sec models, because we are processing input as a sequence, or the input is a sequence and the output also is a sequence. An encoder decoder model has various applications, lots of application in NLP. So one of them is, of course, machine translation, where you have a source text and then you have a target text. Source text is in one language, the target text is in the other language, which is a translation of the source text. So this is a machine translation. So encoder decoder can also be used for example, paraphrase generation. So where the input text is some passage or a sentence, and the output text is another passage that conveys the same meaning as the input text, but in different words. So it's a paraphrase. So encoder decoder can also be used for summarization, where the input, of course, is a document or a passage, and the output is a summary of that passage. In this case also, the input and output lengths are different. So generally, encoder decoder works or is ideal or was designed primarily for the scenarios where the input sequence length was different from the output sequence length. You can also have question answering as an application. So in question answering, you have a question as the input, which is a sequence of words, and the output is the answer to that question. Here again, the input length and the output length may be different. And similarly, you can think of an encoder decoder model being used in a conversational agent, or a dialogue agent, or a chatbot. So in this case, you have two-way communication between two agents, or agent and human being. So you have something that's asked or spoken or written, and then you have a response that is generated. So both of these, the input and output here again might be of different length. So in the case of machine translation, the input and output actually have different languages. That doesn't make a difference. So as long as you have the necessary training data to train it. While in most of the other cases, usually they will be the same language, but different languages models can also be designed. For example, you have an input uh, sentence and the output is a paraphrase. In that case, that wouldn't be really a paraphrase. So in general, usually this, for example, you have a question in English and the answer is in Urdu. So that's also possible as long as you have the training data to do it. So in all of these scenarios, you have an input sequence, which is X. So input basically is X. And then you have a corresponding output, which is Y. And the lengths of X and Y are in general different. So for example, T underscore X would be the length of the input and T underscore Y would be the length of the output. Okay? So these lengths could be different. So, okay, just to reiterate what we did last time. So the encoder decoder model, one of the simplest encoder decoder model for sequences is when you have an RNN for the encoder, and then you also have an RNN for the decoder. So both of them are RNNs. The RNNs, the encoder RNN takes as input X, the input sequence, one by one. Remember, RNN is a entirely sequential model. It takes the input one by one. At each step, it also generates a context or a activation, which is A. So for example, if you have X1 as an input, you also generate A1, which is activation at this particular point. And of course, let's say, so Tx is the total length. At this stage, you also have the Tx being generated. So this is being processed by the input RNN, the encoder RNN. We have already discussed this. So RNN has a number of parameters. The output at a particular time period A is fed into the next time period as input, in addition to the input from the outside world, which is X. So of course, this input length could be of different size. So in the standard encoder decoder model using RNN, we use the last context or the last activation as input or context to the decoder. So the last activation is actually Tx. So this becomes the first activation to the decoder. Okay? And the idea is that this A of the encoder has captured all the information from the source language or the source text. Okay, so now this is being used to condition the decoder. So the decoder knows what the source language is or the source text is, and then the decoder works as a autoregressive generator, which is also an RNN, to produce the output in the target language. So the source, the decoder is basically, while training, uses the target language, while the source uses the encoder uses the source language. So oftentimes we will build a common vocabulary for the source spellings are wrong. Languages. Okay? So you build a common, and we'll talk about this later on as well. So you will have a common vocabulary. Of course, this is theoretically not essential. You can have a separate vocabulary for the source encoder and a separate vocabulary for the decoder or the target language. So the decoder RNN basically is like a language model. It generates the output sentence one word at a time. And we use autoregressive generation. We also use teacher forcing while training. Okay? So that we want to speed up the training. If you don't do teacher forcing, the training might take much longer because each time you might get an error that is then propagated onwards. So we talked about two things last time. The context that is received by the decoder is the last activation of the encoder. So that might lose information from the starting steps or the starting positions of the source language. So sometimes to avoid that, we can use a bidirectional RNN for the encoder. Okay? So that is one option that we can do. If you have a bidirectional encoder, then you have two activations. One from the left to right encoder, the other from the right to left encoder, and then you can maybe concatenate both of them, and that then becomes the context for the decoder. Okay? So in this case, now information would be, you can say, both from the end of the source and the start of the source would be easily available to the decoder. But the more common approach that is used is to use cross attention in the decoder. So we talked about the attention mechanism when we were discussing the transformer. In that particular case, we call it self-attention because attention was based on the same sequence. Here, attention is based on two sequences, or actually one whole sequence and the next sequence. So let's understand this. Of course, I won't go into the math of this. The math of this is essentially or exactly equal to or identical to the one that we did for self-attention. The only difference is that the two sequences that we are talking about are different. So what is the sequence? So let's talk about the encoder. So encoder का sequence are A1 to, of course, A, TX, and this TX can be different. Okay? So one option that you can think of is maybe you can combine all the encoder activations from A1 to ATX and pass it to the decoder. But the problem here is that the length T of the input sequence would vary. And as such, the concatenation of all of these vectors would be of different lengths, which would be difficult to handle in a neural network context. So we would like the information that is passed to the decoder be always of the same length. Okay? So, and of course, this is handled by the cross entropy very nicely. So this is the sequence from the encoder. And then, of course, you have the decoder. I'm not going to write the subscripts. It does become confusing with the notation. So decoder has its own set of outputs, A1 onwards. Okay? So now the attention is between this A1 of the decoder and all of the outputs of the encoder. Okay? So we want to determine how relevant is this A1 in comparison to the outputs of all the steps in the encoder. And we use the same attention mechanism that we talked about earlier. So you have scalar product, you have softmax normalization, you have also normalization with the lengths of the vector. You may have parameters also. You can do it without parameter, but usually we'll have parameters, those WQ, WV, and WK. And those Ws would be applied to these A's. So in the previous context, we had the sequence X1 onwards, and we were applying, for example, we were doing attention for Xi to all the previous context. So in this cross entropy, we are doing A1 or AI of the decoder to all the steps of the encoder from x1 to xdx. Okay? So that's the only difference. So what do we get after this? What do we get after this cross attention? You get a vector, which we can call it a context vector. So what would that vector look like? So if you remember, when we discussed transformers, we generated the output A, I. This was given as alpha ij into Vj. And of course, notations can be a bit confusing. So now in the same context, we are generating C at the ith step of the decoder, the context vector at the ith step of the decoder as alpha ij. I is of course of the decoder, but j is all of the inputs in the encoder into of course Vj. So j are indices over the encoder A's. ठीक है. So of course वहां x थे, यहाँ A's हैं. ठीक है. तो ये जो वेक्टर C है, this vector C now can be defined appropriately. It's just one vector, the fixed length. Its length also can be fixed by choosing the appropriate parameters, W's. उनकी लेंथ फिक्स करके इसकी लेंथ फिक्स कर सकते हैं हम. ठीक है. Of course Vj is what? Vj is let's say we are talking about Aj in the encoder. उस Aj का हमने Vj बनाया हुआ है. किस तरह बनाया हुआ है? Because this is a key. Actually this is a value. So value हम किस तरह निकालते हैं? जो Wv into x करके. Here in this case Wv into Aj. So same approach is used here. So you now have a vector C which is attention based, corresponding to each step of the encoder, and this can be learned for each step of the decoder. Remember, C is I at each step I of the decoder. Okay. So once you have this, so if you include this, then the decoder has just one new element. Remember, in the standard RNN, so decoder RNN. So in the standard RNN, you had AI, the output of some activation function G. W, we have AX, right? So A I minus 1 plus W AA, sorry. Remember, this is teacher forcing, so you do have some X, but it's XI. So A, I minus 1, the previous context, plus BA. So this was the standard equation for the standard RNN. But now we add a new step here. So now we have another vector, which is, you can say, using the same kind of notation, CA into A I minus 1. I minus 1. Oh, sorry, A नहीं होगा. This is C. ठीक है. ये context जो हमने generate किया था through cross attention at this step to the previous step. So this is dash भी नहीं होगा. ठीक. So this now becomes the equation for the decoder, which has that cross attention mechanism included in it, and it has its own parameter, which is WAC. ठीक है. So the standard RNN without the cross attention did not have this term. Now we have added this term where the C is obtained from cross attention at the this of course cross attention is computed at this step with respect to all the steps of the encoder. All right. So that's essentially it. Of course, training is done in the usual way, but as I mentioned last time, it's end to end. The losses are obtained in the decoder. Those losses, after averaging over whatever batch length you have, are then adjusted over the entire network, including the decoder and the encoder. So that's propagated back to the encoder. And all parameters updated through stochastic gradient, including the self-attention, the cross-attention parameters, the parameters of the decoder, the parameters of the encoder. So all of them are updated. Okay, so that's training. And as I said, during training, we use teacher forcing so that we converge quickly. Otherwise, you will have lots of losses. So after generating each step, of course, you'll get a loss, but we know the true value at each step. So let's say, जैसे last time we example दिया था, he studies at LUM. So let's say this is the input sentence. If you generate वो, let's say at your decoder, while you're training, आपके first step में वो generate नहीं हुआ. Let's say कोई और generate हो गया, उसका, let's say उस generate हो गया. But you know it should be वो, but at the next step, you do input X in the decoder as वो. Because आपको पता है वो होना चाहिए था, so that you don't propagate the error of inputting us at that point. ठीक है? So that's teacher forcing, and of course you train, minimize the errors, and once the model has been trained, then of course you can use it to generate the translations. So you have a source text that goes through the encoder. After that, it goes to the decoder. Now, basically, of course, you will be taking the argmax of each output of the decoder and outputting it. And here again, of course, you will be doing teacher forcing as well. But जो output argmax का था, वो next step पे वो input करेंगे. And you will stop when you generate a token which is identifying the end of sentence. Like you can define a token for, let's say, end of sentence. So once this token is generated, or alternatively, you have reached some maximum limit of words in the target language. Let's say you have put in maximum limit of word, let's say 50 words. If 50 words have been generated, you stop. Or once this end of, or otherwise this end of token is generated. Okay. So this is the RNN, standard RNN, the bidirectional RNN, the RNN with cross attention. And we have also talked about training, and we also talked about inference. Okay. So now let's talk about another idea, another concept, which is called beam search. And to motivate this, of course, remember at each step of the decoder, so we have a distribution. We have a distribution over the vocab. ठीक है? So let's say target language मेरी English है, let's say उर्दू से English में कर रहा हूँ, let's say. तो आपके पास English के बेशुमार words हैं, पूरी vocabulary है, A, आसिम है, so on, tons of words हैं, Zulu let's say आ गया. So all of this vocabulary, you will have a probability for each of these words at each step being generated by your decoder. ठीक है? So, and what we typically do is what? We choose the word with highest probability. ठीक है ना? So maybe let's say A was the highest probability word. So you will be outputting A at that point. And then you move to the next step. A then becomes teacher forced as an input, and then you generate the next word and so on. The problem with this is, since this is a sequence, uh, we are actually doing greedy. We are not uh, catering for we are not finding the best output till a particular point by considering all the previous output. We're only considering the current input and the current output. So in this way, we are actually just doing greedy search over the search space. So in the worst case, in the most optimal case, what would happen? So let's say output. So output sequence length is, let's say, 10. Just for example, let's say the T that we use. So let's say is 10. So at each position, you have how many options? You have basically V options, and this typically would be in the tens of thousands. So vocabulary for English, for example, would typically be in the 50,000, 100,000, even larger if it is consists of informal words. So number of possible sequences that could be generated of length 12 would be what? So sorry, length 10 would be 10 raised to power of V. No, उल्टा हो गया, ठीक है. So basically V raised to power of 10, ठीक है ना? Each position पे आपके पास options V हैं और 10 positions आपके पास. So these are the possible sequences, ठीक है? अब इन possible sequence में एक best sequence है, which has the highest probability as a sequence, as a whole sequence. By the way, ये sequences different lengths के भी हो सकते हैं. That's another complexity. ये तो मैंने एक fixed length की बात की है ना, तो they could be of different lengths. But let's say all sequences are fixed length, then this is the possible options that you have. उस possible options में से आपने best ढूंढना है, highest probability वाला ढूंढना as a sequence. So sequence की probability as a sequence की probability किस तरह निकलती है, as we do in language modeling. So basically पहला word का probability आएगी. So whatever that word is, let's say he, given the context, then the next word studies, given the context, and so on. सारे words की आपकी products हो गए. Or if you don't want to use probabilities as products, you can take the log and sum them up. It's the same thing. And find the one that has the maximum probability. So this is a huge or a massive search. But if you are able to do this, then this will give you the optimal sequence as output. Okay? But what are we doing in the greedy search? We are simply saying कि previous word जो था, let's say he था, and we sample the next word and find what is the next most probable word. So let's say उसके बाद let's say कोई word आ जाता है, let's say lums आ जाता है. And then once we have generated lums, we just look at lums and see what is the next highest word. Of course, in RNN previous context आ रहा होता है, but we don't consider that explicitly. It's just implicitly considered through the model. But we just look at the highest probability that comes next. Let's say उसके बाद A आ गया, highest probability का, and so on. ठीक है? And of course, in this greedy search, there is no backtracking. If you get an error, so let's say lums आपके पास erroneous था, तो जब A पे गए तो there is no way of going back and changing lums. तो आपका sequence बड़ा होता जा रहा है with an error. ठीक है? So to find a middle ground between this greedy search and the optimal search, which is very hard or computationally infeasible, we have to do a complete search. So people have proposed what is known as a beam search. Okay. So beam search has a parameter, you can call it K, which is the beam width कह लें इसको, and this k, which is usually a number between you can say 2 to 10, so usually between 2 and 10 in practice. Okay. So in this case, instead of considering only one output at any time step, you consider k outputs at every time step, the top k outputs at every time step. Okay. So we have kind of made it more flexible, although uh, we are not considering all the entire vocabulary, the V possibility. We only considering the top 10 possibility. Of course, as I said, it's not between, it's between optimal search and greedy search, some intermediate level. Okay. So in this way, so what would happen? So let's say, uh, we are generating a target sentence, and at the first step, we found that the top two most probable words are, let's say, he, and the next is, let's say, the. Okay. These again assuming k is equal to 2. If k is greater than 2, you'll take the top 3 or top k in general. So let's say in this example, I'm taking k is equal to 2. So this is the first step. आपके पास दो options हैं. Let's say he की probability ज़्यादा थी, but according to the model, and then the, this is the next, but you are considering both of them. So when you go to the next step, ठीक है, next step में फिर आपने एक दफा उसको ही डाल के आउटपुट करवाना है. सो लेट्स से ही आपने कॉन्टेक्स्ट किया, और इसके बाद आपने दो हाईएस्ट प्रोबेबिलिटी के निकाले. सो लेट्स से एक मेरे पास स्टडीज आ गया और दूसरा इज आ गया. ठीक है, ये मेरे पास विद ही एज द कॉन्टेक्स्ट किया आपने. ठीक है, एंड देन आपने एक डी के साथ भी किया. सो डी के साथ अब आपने जो किया, इसमें जो ऑफ कोर्स ही के साथ किया, तो वो आपके पास पूरी वोकैबुलरी में से टॉप 2 लिया आपने. डी के साथ किया, पूरे वोकैबुलरी से टॉप 2 लिया, तो इसमें दी लेट्स से यूनिवर्सिटी आ गया, और उसके बाद लेट्स से ए आ गया. ठीक है, सो लेट्स से दीज आर टू टॉप मोस्ट. अब इन ऑप्शंस में से यू अगेन फिल्टर डाउन टू 2. ठीक है, सो लेट्स से जो 2 आपके पास फिल्टर हुए हैं, एंड किस तरह फिल्टर करें, द 2 मोस्ट प्रोबेबल. सो लेट्स से आपके पास ही और स्टडीज, ये आपके पास एक ऑप्शन आई इधर, और लेट्स से दूसरी आपके पास आई जो मोस्ट प्रोबेबल थी, इट कुड बी ही इज भी आ सकती है, बट लेट्स से दी यूनिवर्सिटी आ गई. तो आपके पास बीम में फिर दो हो गए, वापस दो कर लिया आपने. पहले भी दो थे, अब फिर दो कर दिए आफ्टर स्टेप 2. बट नाउ यू हैव टू हाइपोथेसिस, टू सीक्वेंसेस. You are left with two sequences. One sequence is he studies, the other is the university. So you continue in this fashion. So next step में आप क्या करेंगे, आप पहला वाला हाइपोथेसिस लेंगे ही स्टडीज, मतलब उसको आपने टीचर फोर्स किया विद ही स्टडीज, और फिर आपने दो ऑप्शंस मोस्ट प्रोबेबल नेक्स्ट लिए. ठीक है, सो आपने इसको ही दिया कॉन्टेक्स्ट में, स्टडी दिया कॉन्टेक्स्ट में, और नेक्स्ट में दो ऑप्शंस लिए. लेट्स से आपके पास एक एट आ गया और दूसरा दी आ गया, लेट्स से. ठीक है, तो ये दो ऑप्शन इधर हो गए. फिर दूसरे के भी दो ऑप्शन आएंगे, दी यूनिवर्सिटी, इज आ गया लेट्स से, एंड एट आ गया लेट्स से. अब इन चारों में से, ऑप्शंस में से, फिर आपने दो फिल्टर कर लें, द वन दैट मोस्ट प्रोबेबल. तो लेट्स से जो दो मोस्ट प्रोबेबल आते हैं, एक आता है ही स्टडीज और एट हो गया, और दूसरा द यूनि मे बी So he studies at, or let's say दूसरा भी जो highest probability है इसी का था, he studies D. Writing is bad today. ठीक है. So now your beam has these two hypotheses, these two sequences so far. अब इन दोनों की फिर आपने extension next step पे देखनी है. एक स्टेप में आपने ही स्टडीज एट फोर्स करना है उसको, फिर नेक्स्ट पे दो बेस्ट देखने हैं. दूसरे में आपने ही स्टडीज इन डी, फॉर ही स्टडीज डी को आपने फोर्स करना है, फिर नेक्स्ट स्टेप्स लेने, एंड देन यू कंटिन्यू इन दिस फैशन. ठीक है. सो एट द एंड ऑफ द, of course these sequences can be a different, where do you stop when you receive the end of sequence token, or as I said, if you reach a maximum length, and the lengths could be different for each of those k hypotheses. ठीक है. So now so this is what beam search is actually. So you are always maintaining two best hypotheses at each step. And what are those two best hypotheses? The two sequences till that point that have the highest probability. And how are you determining that? You are generating the top two outputs at any particular point for each of those two options, and then selecting and filtering back to two. ठीक है. So at the end of the day, you will get k sequences or k options. Of course, if you want to take just one at that point, you can take the one that is the most probable. In some applications, you will like to retain all the outputs. Maybe the other one is also an alternate and correct translation. So you can keep all the k options. Or let's say if you are doing evaluation, जैसे हम अभी थोड़ी देर के बाद देखेंगे, evaluation में आपके पास multiple candidates generate हो सकते हैं, तो आप multiple को evaluate कर सकते हैं and find which one is the best. So as I said, the lengths may be different. Maybe एक hypothesis का end of token 15 के बाद आया है, दूसरे का 3 के बाद आ गया. तो usually इस scenarios के लिए usually जो 3 की probability होगी वो high होगी, because probability जब multiple words की multiply करते जाते हैं थोड़ी होती जाती है. तो usually we'll do normalize it like we do it in perplexity. Remember in perplexity you do geometric normalization. तो यहाँ भी आप normalization कर सकते हैं so that you can compare sequences of different length. ठीक है. So the beam search is thus a trade-off between optimal search, which is computationally almost infeasible, and the greedy search that we typically do, where we select the best or the highest probable word that is generated at each step. And beam search has been found to be quite effective, even if you take k is equal to 5. So if you take k 5, 6, you get pretty much very close results to the optimal sequences. So in that sense, this is a good trade-off. Just one other thing, remember when we were discussing dynamic programming for, let's say, the Viterbi algorithm, in that case, there were two things. One thing was we considered the entire vocabulary in the previous step. Okay? So in that case, that was optimal. Remember जो matrix बनता था VT का matrix था, पूरा उसका column को आप देखते थे किस में से maximum आ रहा है. So that was not K, it was the entire vocabulary V. So that was optimal. The second thing there in Viterbi algorithm was we explicitly made the assumption that the next generated word would only depend on the previous generated word. Okay? So we didn't take the context to the previous level. तो इसलिए वो उस sense में भी optimal है based on the assumption. Here, of course, in general, the sequence will depend on the whole preceding words. The optimality will depend on the entire preceding words. Okay? So this was a beam search. Okay, now let's move on to encoder decoder with transformer. This would be quite brief because we have mostly discussed so the encoder and the decoder, as we mentioned at the start, are sequence models. So they could be any sequence models. So we discussed RNN as a standard sequence model as the encoder and the decoder. You can also have GRU. You can also have LSTM. So these are all sequence models that we have already studied. And similarly, we can also have transformers as the encoder and the decoder, or you can even have them different. Maybe the encoder is RNN, the decoder is transformer, or the transformer is encoder, decoder is RNN. So you can do the uh, uh, you can do whatever you like. So, but of course, transformers have that advantage of being highly parallelizable and somewhat more efficient than RNN. So you can design encoder decoder models or sequence to sequence models with transformers. So of course, with transformers, what would happen? The encoder would be a transformer. So it will process all the input sequence at once and generate all the activations, the A1 to ATX at one step. And then all of that can be concatenated. But as I said, the lengths might be different. But of course, in a transformer, usually the lengths can be the same. You can feed it to the, because in a transformer, what happens? You have to, I think I didn't mention this before. So a transformer needs to have a fixed input size. Okay, na? Unlike a RNN, so you can feed in like say a sentence of 200 words or 5 words or 20 words and so on. But in a transformer, you need to have a uh, fixed input to the network. Otherwise, those matrix operations will not work. So usually, what we do is we do the issue of what is called uh, uh, so I have forgotten the word. So basically, if you have a sentence that is, so you fix a length for input. Okay. So if a sentence is longer, you basically clip it to the length. Okay. So if sentence is shorter, so we pad the remaining positions. So the padding would be a specific token with a fixed representation. So that would be reserved for padding. So it means that this is a padded word. So let's say aapne, so for example, in one of the standard transformers, we have 512 input. So if you have a passage that is 40 words long, so you will have 40 words initially, and then you will have 512 minus 40 paddings, okay, as input to the transformer. On the other hand, if you have 600 word input, then you will truncate to 512, okay, as input. Of course, this is there's some loss of information. This loss of information has been found in practice not to be a big impact. So some people say that, of course, an RNN can process any sequence of any length, while a transformer has to be packaged into some, you can say, fixed window. But in practice, it doesn't make much of a difference. Performance still improves through a transformer. Okay. So this was about the input. So the encoder transformer would generate the activations for those 512 inputs. For example, these can be fed directly to the decoder transformer as a context, or so that could be done, and then you do auto generation with teacher forcing for the decoder transformer. Or you can feed this, or you can you can have a cross attention mechanism just as we did for RNN, and then the C that you get for the cross attention is then fed to the transformer. Okay. So actually, I think usually in a transformer you have self attention, which is always present. So in addition to that, you have a cross attention, which is attention between the decoder and the encoder. So both of these are processed separately and then combined to generate the output. Okay. So I think that's essentially it. So you can use transformers as sequence to sequence models as well. And you can process them in somewhat parallel fashion, speed up the computation. All right. So any questions? Okay, so now let's move on to evaluation, and we'll come back to some, you can say, um, further concepts, I think, later on. So evaluating machine translation. So as in most NLP tasks, you have two ways of evaluating any task. One is, of course, human evaluation, and the other is automatic evaluation. Okay? And of course, in general, for most NLP tasks, human evaluation would always be considered more of greater quality, but of course, it would take more time and it would also cost more. But in terms of quality, human evaluation is always considered better than automatic evaluation. So let's first talk about human evaluation. So we usually evaluate our translated text. So generally what happens actually in evaluation, in machine translation. So when you're testing, you have a candidate, let's say C, that is generated uh, by the system, by your model. And then you have a reference R. So this is so let's say we are translating into English. So the true, let's say, translation is he studies at LUMS. And let's say that's a true or reference translation. And let's say the system generates he studies in LUMS. Okay? So that is C, that is generated by our system. And the true is he studies at LUMS. So these are the two outputs that you typically get. And of course, for human evaluation, you may even have so this is of course the target. ठीक है ये दोनों candidate और reference जो है ना ये target है. But you can also have the source language. And especially if you're doing human annotation or human evaluation, तो उनको हम source का भी दे दें, especially if they are bilingual, they know both languages. तो हमको उसको source भी दे देंगे, उनको system generated translation भी दे देंगे, उनको actual translation भी दे देंगे. ठीक है? And then we'll ask them to make judgment. So we typically evaluate along two dimensions. The one is adequacy. There might be other as well, but these are the most popular. And the other dimension is fluency. Okay. So we evaluate along these two dimensions. What is adequacy? Adequacy basically means that how well does the translation capture the meaning of the source. So is the meaning that is presented in the source language completely captured in the translated text? So that is captured by adequacy. And fluency basically checks how fluent is the translated text, how natural, how grammatically correct, how readable, how clear is the translated text. Okay. So adequacycally, of course, you will need to provide the source, and your reviewer typically would need to be bilingual. तो फिर ही वो एडिक्वेसी पता चलेगा ना, या आप बाइलिंगुअल नहीं है तो फिर आप सिंपली उनको टारगेट लैंग्वेज की जो जनरेटेड टेक्स्ट सी देंगे, कैंडिडेट देंगे और आर देंगे, एंड वी अज्यूमिंग दैट आर इज कंप्लीट, and then basically the human annotator determines whether C adequately captures all the information in R. Okay. So in both of these dimensions, we will have some scale, some rating scale. So let's say from 1 to 5, 1 might be inadequate or 1 might be totally not fluent, and 5 would be adequate and 5 could be highly fluent. Or here you ask maybe multiple annotators, multiple human beings to evaluate the translation, and then you can take the average and then maybe also apply some other stats that are appropriate for human evaluation. For example, you can find inter-rater coherence or inter-rater, you can say, yeah, coherence is fine, or correlation you can say. So meaning that if there is some example on which multiple raters differ, it means that that example itself is hard, and you might want to give lesser weightage to that evaluation. ठीक है ना, तो इस तरह की चीजें आप कर सकते हैं. So for example, a kappa stat is often used for inter-rater correlation. So you can look up kappa statistics is commonly used for evaluating the coherence or correlation between multiple annotators. And there are others as well, actually. Okay. So, and usually, of course, nowadays you have crowdsourcing. So you can outsource your task to the crowd and ask multiple annotators to evaluate your translations and collect the stats from them on adequacy, on fluency, and then do the analysis and generate a final result based on those things. Of course, when you outsource it to the crowd, usually the quality of the annotators might be of high variability. Some might be good, some might be really bad. So you need to do deeper analysis and maybe filter out those annotators that always or consistently do bad evaluations. Okay. So, so by the way, in NLP in general, evaluation is extremely important. So if you are doing research in NLP, so evaluation is extremely important. So you need to do human evaluation, you need to do automatic evaluation, and thirdly, you often have to do error analysis, meaning that the errors that are generated by your system, you need to look into those and then maybe backtrack to discuss why these errors were generated, and maybe use that information to maybe fine tune your model. So evaluation is very important. So this was human evaluation. So what about automatic? Okay. So for automatic evaluation, we have a number of measures. Some of them are older, but sometimes they're still used. So we will discuss all of them briefly. So let me mention those. We're also running out of time, actually. So let's see. So there is one called Rouge. This was actually originally designed for summarization. Uh, and then we have bilingual evaluation under study, or Blue Score. This is another measure. Uh, and then there's another measure that's become more popular, is simply called character F, or character precision, or CHRF. So automatic evaluation, this first category of measures is based on overlap of words or characters. Okay? So overlap between what? Between the candidate and the reference. The reference is assumed to be correct, and candidate is the one that's generated. So we find overlaps between words or characters in candidate with the reference, and then based on those overlap and maybe precision, recall, and F, we compute Rouge, Blue, or CHRF. So that's one category. The other category is based on similarity, or so I should say the other category is based on, yeah, I think similarity is fine, based on similarity. So in other words, similarity between the candidate and the reference uh, text. And this similarity usually based on embeddings. Remember, we talked about embeddings and representation that are much richer. So we don't simply do similarity like synonyms and so on, but this is based on embeddings. So there are some techniques in this category as well. One of them is actually prediction based. We'll discuss this next time. And the other is simply similarity based, you can say. So similarity based. So you can say, in a way, in one case you're using a classifier, in the other case you're not using a classifier, simply doing comparisons of similarities. But in both case, explicitly or implicitly, similarity is involved, or the notion of embeddings is involved. So these are the two broad categories of automatic evaluations. And let's see, we are almost out of time. So let me just start with Rouge very quickly, and then you get ready for the quiz. So Rouge basically stands for recall oriented, Rouge. U is understudy. Understudy is quite commonly used. Gisting evaluation. So gisting, of course, is for summary. So this was proposed originally for summary, and as the name suggests, it's also based primarily on recall. Although extensions do use precision as well, but primarily they use recall. So I think I'll just name these and then stop. The other one is BLEU, Blue Score. So this basically stands for bilingual evaluation under study. So this was an extension to Rouge, and this was primarily designed for translation, and this is primarily based on precision, not recall. And then we have CHRF. This is character based. F score. So F score, of course, includes both precision and recall. Okay. So we will discuss this next time. So I think time for quiz is almost here. So you can get ready for your quiz. So this is your last quiz. I'll be dropping 2 low scores from your quizzes to compile the final grade for your quizzes. So any questions? Any questions? So this was lecture 24. We have maybe 3-4 lectures left. So maybe 2 or 3, not probably 4, because uh, the week after next week is actually the extra week. So we will be primarily be finishing this up, and then we're talking about BERT, which is contextual embeddings, and maybe one quick lecture on semantics, and that will pretty much be it for this semester. Okay, any comment or question?